Hi, my name is Juan Perdomo, and today I'll be talking about my recent work together with John Miller and Tijana Zrnic, titled Outside the Echo Chamber, Optimizing the Performative Risk. So our work is motivated by the observation that oftentimes when machine learning is deployed in practice, particularly within societal system that involves some sort of decision making, these machine learning platforms exhibit strong feedback loops. An example of such a feedback loop happens within credit scoring. We might imagine credit scoring as following this process by which a bank collects individual data regarding people's income, credit history, whether they've paid back loans or not in the past. With this data, then they create a predictive model which attempts to determine the probability with which an individual will default on a particular loan. Given this probability of default, the bank then sets an interest rate, and this interest rate then influences the final outcome as to whether that person will or will not pay back the bank's loan. What I'd like to highlight about this loop is that the bank's predicted probability of default affects the true probability of default by helping inform the interest rate or the action of the decision maker in this context. If the bank sets a very high probability of default or predicts that the individual is likely to default on a loan, then the bank will set a higher interest rate, and therefore the true probability of default is higher since paying back a loan with a high interest rate is much harder. And clearly the opposite happens if the bank predicts a low probability of default. They'll have a lower interest rate, and then the true probability of default will be lower. Furthermore, this realized outcome goes back into the data set of the bank and affects the classifier predicted at the next day, generate the next day or the next year, whenever the bank retrains its models. In order to assess and understand these kinds of settings where there's feedback between the predictive classifier and the observed distribution of our data, we've developed together with collaborators this performative prediction framework that tries to capture these kinds of feedback loops. The key feature of performative prediction relative to a classical setting such as supervised learning is that there is no longer a fixed distribution over the observed data. Rather, each predictive model is associated with a potentially unique distribution over instances. The key phenomenon that it tries to capture is that predictive models lead to new impact decision making and lead to model-induced distribution shift, which we call performative effects. Relative to supervised learning, in performative prediction, we fully acknowledge the fact that decisions change the state of the world, which generates new data that feeds back into our predictive models, whereas in supervised learning, this arrow cannot exist, right? Our predictions cannot affect the observed distribution since there's just a single static distribution. Once we recognize these feedback loops, we start to notice them everywhere. For example, in election forecasting, if we predict that a candidate is likely to win an election by a landslide, that might deter that person's supporters from turning out to vote, thereby negating the margin of victory or making it smaller. Similarly, in climate forecasting, whenever we predict what the climate will look like 100 years from now, that influences policy decisions today, which affect the future state of the climate and alter the very thing that we're predicting on. A more mundane example is when we commute to work, we open up a Maps app, which will give us an ETA for a particular route. If the route tells us that a route has low ETA or low travel time, then many people are more likely to take that route, thereby changing traffic patterns and affecting the true observed travel time. In this paper, we study the problem of finding accurate classifiers that work well even in this performative, even under settings where there are strong performative effects. The main challenge that we overcome is that even for simple classifiers, simple losses, which are easy to solve in classical settings such as supervised learning, these problems can become non-convex in performative settings due to the effects of feedback and distribution shift. Our main results are that we identify a set of conditions under which the performative risk is convex and has tractable to optimize, and we introduce a new two-stage procedure for efficiently computing these accurate classifiers. Thanks so much for paying attention, and for more information, please come to our talk or watch the longer talk, or happy to chat at the conference. Thanks.